The National Electrical Code, NEC, does have stipulations regarding the use of a 3-conductor cable with separate neutral and ground conductors in a 3-phase, 4-wire distribution system. NEC 300.3b states that conductors of the same circuit, including grounding conductors, shall be grouped together and enclosed within a raceway, cable, or other suitable enclosure. This requirement is in place for safety reasons. Grouping all circuit conductors together minimizes the impedance of the circuit, which is important for proper operation of overcurrent protection devices. When a fault occurs, the impedance of the fault current path must be low enough to allow sufficient current to flow to trip the breaker or blow the fuse quickly. If the neutral conductor is run separately from the phase conductors, the impedance of the fault current path increases, potentially delaying the operation of the overcurrent protection device and increasing the risk of fire or shock. Secondly, keeping the conductors close together helps to cancel out the magnetic fields created by the current flowing in each conductor. This reduces inductive reactance, which can cause voltage drops and other problems in the electrical system. Thirdly, grouping conductors together also reduces the risk of physical damage to the conductors. When conductors are run separately, they are more likely to be exposed to abrasion, impact, or other types of damage. The NEC requires that all conductors of a circuit be grouped together for safety reasons. This prevents accidental contact between conductors of different circuits, which could lead to a short circuit or electrical fire. In the case of a 3-phase, 4-wire distribution system, the neutral conductor carries the unbalanced current from the load. If the neutral conductor is separate from the 3-conductor cable, it would not be grouped together with the phase conductors and could therefore pose a safety hazard. If using a 4-conductor cable isn't possible, an alternative solution is to use a 3-conductor cable with a separate 4/0 bare copper equipment grounding conductor, or EGC. The EGC would be connected to the neutral bus at the panel or disconnect, and it would serve as the neutral and grounding conductor for the circuit. This solution is permitted by the NEC and provides a safe, code-compliant way to distribute power. NEC 250.148 states that an equipment grounding conductor shall be run with each circuit conductor and shall be sized in accordance with Table 250.122. It is essential to ensure that the impedance of the ground fault current path is sufficiently low to facilitate the quick operation of overcurrent protection devices. If the impedance is too high, it can impede the flow of fault current, potentially delaying the tripping of a breaker or the blowing of a fuse. This delay increases the risk of electrical shock or fire. Secondly, the equipment grounding conductor must be properly sized to handle the maximum ground fault current that could occur. The size of the EGC is determined by Table 250.122 in the NEC, which is based on the size of the overcurrent protection device protecting the circuit. Thirdly, the equipment grounding conductor must be securely connected to the equipment grounding system. This ensures that the fault current has a low impedance path back to the source, allowing the overcurrent protection device to operate quickly. In a 3-phase, 4-wire system, the neutral conductor provides a return path for unbalanced currents. The neutral carries the difference in current between the 3-phase conductors, and it is essential for the proper operation of many types of loads, especially those that are non-linear. If the neutral conductor is not properly sized or installed, it can result in voltage imbalances, overheating, and other problems. The NEC provides specific requirements for the sizing and installation of neutral conductors in 3-phase, 4-wire systems. In many cases, the neutral conductor must be the same size as the phase conductors. It is essential to consult the NEC and other applicable standards to ensure that the electrical system is designed and installed correctly. Using a separate equipment grounding conductor as a combined neutral and ground requires careful consideration to ensure compliance with the NEC. The NEC addresses specific requirements for sizing, installation, and bonding of grounding and bonding conductors. The equipment grounding conductor must be sized according to NEC Table 250.122, based on the size of the overcurrent protective device in the circuit. It must also be continuous and have sufficient capacity to carry the available fault current. The EGC must be connected to the neutral bus in the panel or disconnect. This connection must be made in a manner that ensures a low impedance path for fault current. The EGC must also be bonded to any metallic enclosures or other conductive parts that could become energized. This bonding ensures that these parts are at the same potential as the neutral, reducing the risk of electric shock. There are specific requirements in the NEC for grounding electrode systems. A grounding electrode system provides the connection to the earth for the electrical system. This connection helps to stabilize the voltage of the electrical system and provides a path for fault current to return to the source. The grounding electrode system must consist of one or more grounding electrodes, such as a ground rod, ground plate, or metal underground water pipe. The grounding electrodes must be connected to the electrical system with a grounding electrode conductor. The size of the grounding electrode conductor is determined by NEC Table 250.66. The grounding electrode system must be installed in accordance with NEC 250.50 through 250.70. The requirements for bonding are found in NEC Article 250, Part 5. Bonding is the process of connecting all metallic parts of an electrical system together to create a low impedance path for fault current. Bonding helps to ensure that all metallic parts are at the same potential, reducing the risk of electric shock. Bonding is required for metallic raceways, metallic enclosures, metallic equipment, and other metallic parts that could become energized. The bonding connections must be made with bonding jumpers or other approved methods. The size of the bonding jumpers is determined by NEC Table 250.102. To ensure electrical safety and code compliance, it is crucial to carefully follow all applicable requirements in the NEC. The NEC is a comprehensive set of rules and regulations that cover all aspects of electrical installations. It is essential to have a thorough understanding of the NEC to design and install electrical systems safely and correctly. It is always recommended to consult with a qualified electrical engineer or electrician when working on electrical systems. These professionals have the knowledge and experience to ensure that the electrical system is installed in accordance with the NEC and other applicable standards. Additionally, local codes and regulations may impose further requirements beyond the NEC. It is important to be aware of and comply with these local requirements to ensure that the electrical installation is safe and legal. The requirements for electrical installations can vary based on the type of occupancy, such as residential, commercial, or industrial. Each type of occupancy has unique electrical needs and potential hazards, and the NEC provides specific requirements for each. For example, the requirements for grounding and bonding in a hospital are different from those in a residential dwelling. It is important to understand the occupancy classification of the building and to follow the applicable requirements in the NEC. Furthermore, electrical equipment must be listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories or ALL. Listing and labeling indicate that the equipment has been tested and found to be safe for its intended use. It is important to only use listed and labeled equipment in electrical installations to ensure safety and compliance with the NEC. Changes and revisions to the NEC occur every 3 years. It is important to stay up to date with the latest edition of the NEC to ensure that electrical installations comply with the most current requirements. Many resources are available to help electrical professionals stay informed about the NEC, including training courses, seminars, and publications. Improper electrical installations can create a multitude of hazards, including electric shock, fire, and equipment damage. Electric shock can occur when a person comes into contact with an energized conductor. The severity of the shock depends on the amount of current flowing through the body, the path of the current, and the duration of the contact. Electric shock can cause muscle contractions, burns, and even death. Electrical fires can be caused by overloaded circuits, loose connections, and damaged wiring. Electrical fires can spread quickly and cause significant damage to property and injury to people. Equipment damage can occur when electrical equipment is not properly installed or maintained. Overvoltage, undervoltage, and other electrical problems can damage sensitive electronic equipment. Periodic inspection and testing of electrical installations is crucial for identifying and correcting potential problems before they lead to hazards. Electrical inspection should be performed by qualified professionals who have the knowledge and experience to identify and assess electrical hazards. Electrical testing can include insulation resistance testing, current impedance testing, and other tests that can reveal hidden problems in the electrical system. Proper maintenance of electrical equipment is also essential for preventing problems. Maintenance can include cleaning, tightening connections, and replacing worn or damaged parts. By following these best practices, electrical installations can be kept safe and reliable for many years. Ultimately, electrical safety is a shared responsibility. Electrical professionals, building owners, and occupants all have a role to play in ensuring that electrical systems are safe and well maintained. By working together, we can prevent electrical hazards and protect people and property from harm.